We defined uniform circular motion the other day as circular motion in which the object that was moving in the circle is going at a constant speed. Now, just because it's going at a constant speed doesn't mean it's going at a constant velocity. Can anybody explain to me what the difference is there? Can anybody explain to me why it can be moving at a constant speed, but yet not necessarily at a constant velocity, Rucker? Yeah, it's changing direction, right? It's going in a circle, it's changing direction. Rucker said it's moving back and forth on the x and the y axis. It is, but the simple way to say that is it's changing direction. So because velocity is a vector and the direction is changing, its velocity is changing, but yet its speed is not. If its velocity is changing, then it's accelerating, because we define acceleration as the rate of change of velocity, not the rate of change of speed. Speed stays the same. Velocity changes, we still have an acceleration. Now, it's not an acceleration that means it's speeding up or slowing down. It's an acceleration in which the direction is changing. The direction of the acceleration is always pointing in one particular direction. What is that direction? Which way does the acceleration always point? Toward the middle, toward the center. We call it a centripetal acceleration. Centripetal means center seeking. So we've got a center seeking acceleration, an acceleration that is always acting toward the center of the circle. So if this is our object moving around in a circle like this, at this point, moving counterclockwise, its velocity would be like this. At this point, its velocity would be like this. Its velocity is always what we call a tangent to the circle. But its acceleration at each of those 3 points would be toward the center of the circle. Because acceleration, centripetal acceleration, that is, center-seeking acceleration, always points toward the center of the circle. So the green marker there is going to be my velocity at a given point. The red marker is going to be my acceleration at a given point toward the center of the circle. Now, we gave you an equation yesterday for the centripetal acceleration. We said AC, centripetal acceleration, and then we put those little lines on either side of that, meaning the absolute value. It's a vector, but we're not going to get the direction out of it by this equation. We don't need it because we already know the direction. It's toward the center of the circle. It's equal to v squared over r. What did v stand for again? No. Speed, not the velocity, because the velocity is changing. The speed isn't changing. That's how we're going to find the acceleration, with the speed. So it's speed squared over r. R, of course, is the radius of the circle, which is going to be measured in meters. What units do you think you're going to get for centripetal acceleration? I'll give you a hint. It's not rocket science. You guys can figure this out really, really easily. What units do you think we're going to get for the acceleration? Meters per second squared, right? Of course, it's going to be the same units as any other acceleration we have. Now, we also talked about a centripetal force yesterday, a force that acts toward the center of the circle. A center-seeking force. If we have an acceleration that points toward the center of the circle, then we must have a force that acts toward the center of the circle as well, because F is equal to m times a. Now, I'm not going to redraw this diagram, because if the acceleration at these 3 points points towards the center, then the force at those 3 points will point in exactly the same direction. The equation? Well, F is equal to m times a. We know that, right? But a, we know from just a minute ago, is equal to v squared over r. So I'm going to take my equation F is equal to m times a and replace a with my centripetal acceleration equation. The centripetal force becomes mv squared over r. This one appears on my data sheet. This one appears on my data sheet. Now, the question I get a lot of times is, depends on how I write it down. Sometimes I write it F is equal to mv squared over r, and sometimes I'm not even thinking, I write it like this. What's the difference between those two equations? None. None. M times v squared over r is exactly the same as mv squared over r. Does that make sense? I don't care how you write it. Okay, I don't care how you solve it. Okay, I don't care whether you go m times brackets v squared over r, or whether you go m times v squared and then divide all that by r. It means exactly the same thing, and you get the same answer every single time there. What would the units, do you think, be for centripetal acceleration? This isn't rocket science either. Not centripetal acceleration, sorry, centripetal force. It's going to be newtons. Okay, the units for any force is newtons, including centripetal force. Now, do you remember what we said about centripetal force yesterday, just before we left? We talked about it not being a fundamental force. It's not a fundamental force like gravity is, or like tension is. It's a force that's always caused by something else. You drive a car around a turn, there's a force of friction acting on the wheels of that car. That's what provides the centripetal force. Swing the keys around my head, there's a force of tension in the string that's pulling these keys in a circle. Okay? That provides the centripetal force. The moon goes around the Earth. There's a force of gravity that acts between the moon and the Earth. That provides the centripetal force. Finally, the electron goes around the nucleus of an atom. There's an electric force that keeps the electron orbiting around the nucleus. That electric force provides the centripetal force. Centripetal force is never a force on its own, like friction is, or electric force, or like gravity is, or like tension is. It's always a force that's caused by something else, like friction, or gravity, or the electric force, or the tension. Does that make sense? Can you name something else that might cause a centripetal force besides those four that I mentioned? Right? Tension, gravity, centripetal force. What was the other one I mentioned? Electric force. Think of some other situation where an object is moving in a circle and therefore experiences a centripetal force, but of course it's got to be caused by something. Another centripetal force that we can have is the one that we just saw in the video that we just watched, and that is the force of lift, right? The airplane was going on its side around a turn. Didn't end up good for that airplane. While it was going in that turn on its side, as it was going in a circular fashion kind of around that turn, there was a force of the wings, the force acting on the wings, pulling it in towards the center. That's a centripetal force, but that centripetal force is caused by the force of lift, that this time isn't pulling it upwards, it's pulling it sideways toward the center of the circle. So there's a million different forces that can cause the centripetal force, but one of them always has to cause it. Because centripetal force never acts on its own. It's always caused by something else. All right. Let's take a quick look at the centripetal force, or centripetal acceleration, I should say, on the outer edge of a DVD or a CD or a Blu-ray disc. A DVD specifically has a rotational period of 0.10 seconds. That means it makes one complete revolution in 1/10 of a second. Spins around 10 times per second, basically. Has a diameter of 12 centimeters. We're going to find the centripetal acceleration at the outer edge of the disc. What's the radius? 6 centimeters. Good. We have a diameter of 12 centimeters. That's not what we want. We want the radius. 6 centimeters, or 0.0600 meters. We have a period here of 0.100 seconds, and we want to find the acceleration. The centripetal acceleration we know is equal to v squared over r, but unfortunately we don't have v. So we've done not this per se, but we've done enough physics this year so far that we know where we're going with this, right? We start with an equation that doesn't seem to work for us. We're missing something. Well, we find the thing that we're missing. How do we find v? The speed at the outer edge of this disk as it moves in a circle. Okay? D over t, yes, it's d over t. D is the circumference of the circle, or 2 pi r, and t is the time around the circle once, which is period, right? So we get 2 pi r over t becomes 2 times pi times 0.0600 meters divided by the period of 0.100 seconds. We get 3.7699 meters per second. Now we're going to take that number and plug it in here, 3.7699, make sure we square it, divide it by r, 0.0600. And when we do that, we get 236.9, or rounded to 3 digits, it would be 237 meters per second squared. That's a pretty high rate of acceleration. Obviously it's a DVD. You can't stand on the edge of a DVD as it spins around. It's 12 centimeters from side to side. Okay, it also spins really, really fast. If you were able to stand on the edge of a DVD as it spun around, you would experience an acceleration of 237 meters per second squared. The acceleration that you normally experience is about 10, right? 9.81 meters per second squared. That would mean that you would feel a force that is about 24 times the normal force of gravity that you feel. That would mean, you guys have heard the term G-force before, right? That would mean that you would be pulling about 24 Gs. Okay, that's a lot. You're going to have questions at West Edmonton Mall next week, next Tuesday, where you're going to have to find the number of Gs that you experience while on the roller coaster. Listen carefully. What you're going to do with that is divide the acceleration that you experience by 9.81. You got that? So if you experience an acceleration of 50 meters per second squared, divide that by 9.81, and you're going to get about 5 Gs. Okay? And there's going to be a point on the roller coaster, the Mindbender, where you're going to pull almost 5 Gs. Okay? It's 4 point something Gs. I'm sorry? Well, it's not the CD per se, it's the speck of dust on the edge of the CD or whatever it is. It's at the edge of the CD that you're talking about how heavy it feels, okay? Essentially, anything on the edge of the CD would feel about 24 times heavier than it really is. So for you, if you weigh, let's say for argument's sake, you're going to weigh more than this, but let's say you weigh 50 kilograms, your mass is 50 kilograms. You would feel like you weighed 1,200 kilograms in that case. And you're going to really notice that next week on the Mindbender. It's, well, 24 Gs would, yeah, I mean, that would certainly make you pass out. And probably if you sustained it for any more than a couple of seconds, it'd probably kill you, yeah. You're not going to have that many on the roller coaster next week. You might experience up to 5, and you will feel extremely heavy. So much so that you won't even be able to keep your head up. So much so that there's, at one point on the roller coaster, there's a double loop. Like this. You go around the double loop like this. By the time you start going through the second loop, most of you will start blacking out. Most of you, your peripheral vision will start disappearing. It'll get narrower and narrower and narrower and narrower to the point where you can't see anything. Your eyes are wide open and it's completely black. You're conscious, but your eyes are wide open and it's completely black. That's happening because you're experiencing in that place about 3 to 4 Gs. And you're experiencing it for several seconds. And essentially the blood is being sucked out of your head. So you're in that process of starting to pass out. If you were in that loop for another couple of loops, you'd probably actually pass out. No, you're still conscious. You still know what's going on. You just can't see anything. You're temporarily blinded. But if you sustained it for more time, you probably would pass out though. But nobody's going to pass out for that short of a period of time. All right, let's take a couple minutes and work on the questions on page 255, please. All right, let's take a look at another example now that you've had a chance to work on those. 5.4 says, determine the magnitude this time of the centripetal force, not acceleration like the last question was, this time centripetal force, exerted by the rim of a dragster's wheel on a 45 kilogram tire, assuming the radius of the tire is 0.480 meters. And it's rotating at a speed of 30 meters per second. Let's break down our givens here. We've got a mass of 45.0 kilograms. We've got a radius here of this tire of 0.480 meters. And we've got a speed of it of 30.0 meters per second. We want to find that centripetal force. On your data sheet, we know that centripetal force is equal to mv squared over r. Whether it's m times v squared over r or mv squared over r doesn't make any difference in the world. So let's do our thing here. Mass is 45.0 kilograms. The speed is 30.0 meters per second. Square that, and the radius is 0.488 meters. Sorry, that's 0.480 meters. Thank you. 0.480 meters, not 0.488. For this one, we get a force of 84,375, or we're going to round that to 3 digits. It's going to be 8.44 times 10 to the 4. And what would the units be for that? It's going to be newtons, right? Anytime we have a force, it's going to be newtons. Okay, I don't think that you're going to have any trouble at all with these questions on page 256 if you were able to do those acceleration questions on the last page. These are no harder. They're almost the same thing, in fact, except that you've got to stick an m in there as well, a mass in there as well. It's not just v squared over r, it's m times v squared over r. Because I don't think you're going to have a whole lot of trouble with it, we're going to do one more example before I give you a chance to work on those. The last example that we're going to do today says, it's on page 259, it says, determine the maximum speed at which a 1,500 kilogram car can round a curve that has a radius of 40 meters if the coefficient of static friction between the tires and the road is 0.60. This is a harder question. What's the maximum speed that it can go around if we have friction with a coefficient of friction of 0.60? Well, let's write down some givens here. We want to find speed. We've got a mass here of 1,500 kilograms. We've got a radius of this turn of 40.0 meters. And we've got a coefficient of friction of 0.60. We know that when it's going around a turn, it will experience a centripetal force. It's mv squared over r. But that's not enough to get me speed, because I don't know what force is. Listen very carefully. Okay, we've said this a number of times. Something always has to cause the centripetal force. If we don't know what the value of the centripetal force is, then maybe we can get the value of whatever it is that's causing it. What is it that's causing the centripetal force in this question? If something wasn't there, this would not go in a circle. What has to be there in order to cause this to go in a circle? Well, yes, the car. What force has to be there? The curve, but what is it that's causing the car to go in a curve directly? The centripetal force, which is caused by friction. Right? If you don't have friction, there is no centripetal force. And if friction is not there, it's not going to go in a circle, and there is no centripetal force. So, look, we got M, we've got R, we want to find V, but we don't have F. So let's get F. The centripetal force is caused by friction. So let's find the value of friction and then plug it in for the centripetal force. Mu is 0.60, and the normal force, we're going to assume a flat horizontal curve here. We're going to say the normal force is m times g, or 1,500 times 9.81. Here we get a force of 8,829 newtons. That's my force of friction, but since friction causes the centripetal force, then that's also going to be my centripetal force. Now all I'm going to have to do is rearrange this to solve for V. Let's take the R up by multiplying. Let's take the M down by dividing. And how do we get V by itself there now? Square root it now, right? So V is equal to the square root of FC times R over M. We know the value of FC now. We didn't when we started the question, but we do now. 8,829 times the radius of 40 meters divided by the mass of 1,500. We get a speed here of 15.3 meters per second. So anything below that speed, this car is able to stay on the turn. Anything above that speed, what's going to happen? The car is going to skid off the road, right? Because the force of static friction isn't big enough to provide that centripetal force. It needs that centripetal force to stay on the turn. But if you're going any faster than that, then friction isn't going to be strong enough to supply that centripetal force, and it's no longer going to go in a circle. Sorry? Okay, here's your homework for the weekend. I want you to finish the questions, please, on page 255, and I want you to do the questions on 256 and 259, please. So there's 3 sets. One set you've probably pretty much finished. I want you to finish up that set and the other 2 sets, please. Have a good weekend, everyone, and we'll see you guys Monday morning.